Okay, number 9, we want to know if this function f of x is continuous at x equals 2. All right, here are the 3 conditions for a function being continuous at x equals c. All right, so the first one says that we'll use 2 instead of c, that f of 2 has to exist. Well, that doesn't because of the x minus 2 in the denominator. 2 is not in the domain of this function. 2 would make the denominator 0. So 1 is not true. Okay, so that's right, 1 not true. So that means the function is not continuous. All right, just from that. Let's look at number 2 though, that the limit, does the limit as x goes to 2 exist? Well, the limit as x goes to 2 is infinity and minus infinity. Infinity if x is bigger than 2, and minus infinity if x is less than 2. So this is an infinite limit, what we were calling an infinite limit. Infinite limit means does not exist. That's a specific example of that's one type of limit that does not exist. All right, so 3 obviously can't be true. So this is definitely not continuous at x equals 2. Oh, let me mention also that it's not removable because 2 is not true. The limit does not exist. If a discontinuity is removable, then 2 has to be true. The limit must exist. Not removable since 2 is not true. Number 10, we're taking the limit as x goes to, in number 10 we want to know if f of x is continuous at x equals 2. Well, f of 2 exists. The only x value that's not in the domain is x equals minus 5. So 1 is true. All right, how about 2? The limit as x goes to 2. Well, the limit as x goes to 2 is obtained by just substituting in 2 for x, because we do have a rational function and 2 is in the domain, so we can just substitute in. That's one of the limit rules. Okay, I think it was the third limit rule. All right, so the limit exists is actually equal to f of 2, which is 0. So let me just write what it's equal to. The limit as x goes to 2. Here we can just substitute in because 2 is not a 0 of the denominator. So that's 2 minus 2 over 2 plus 5, 0 over 7, which is 0. Okay. So the limit exists, and so this one's true. And number 3, the limit is equal to f of c. Number 3 is also true. Okay, the limit is 0. And f of 2 is 0. So all 3 conditions hold, and f of x is continuous at x equals 2. Okay, here we want to know again, is f of x continuous at x equals 2? Well, 2 is not in the domain because of the x minus 2 in the denominator, so 1 is not true. All right, how about 2? The limit as x goes to 2 of x squared minus 4 over x minus 2. Well, when we take the limit, we can reduce. It's the same as the limit as x goes to 2. Let's see, let's reduce this. This is x plus 2 times x minus 2 over x minus 2. So we can cancel. And now it's the same as the limit as x goes to 2 of x plus 2, which we get by just substituting in. That limit is equal to 4. All right, so 2 is true. The limit exists. 3 cannot be true because f of c does not exist. So 3 is not true. Okay, 4 cannot be equal to something that doesn't exist. So, all right, but since 2 is true, that means that, in other words, 2 true implies that the discontinuity is removable. All right, so we have 1 not true immediately means it's not continuous. As long as one of these is not true, it's not continuous. Okay, so our function is not continuous at x equal 2, but it is removable. Okay, number 12, again, we want to determine if f of x is continuous at x equal 2. All right, first number 1. Number 1 is true. F of 2 exists. Just substitute into this top expression because of the x less than or equal to 2 here, and we get 2 plus 5. Okay, so 1 is true. All right, how about 2? Well, 2 we'll see is not true. In other words, this limit doesn't exist. A quick way of checking is just substituting in 2 here and here. Here we get 7, and here we get 3 times 2 is 6. 6 plus 4 is 10. Since these are not equal at 2, then the limit can't exist. But we have to really go through the entire explanation. We have to say the limit as x goes to 2 from the left of f of x is equal to, substitute into here, 2 plus 5 equals 7. And the limit as x goes to 2 from the right of f of x is equal to, okay, substitute into here, and we have 3 times 2, that's 6 plus 4, equal 10. All right, and so these are not equal, which implies that the limit as x goes to 2 does not exist. So that's why 2 is not true. So 3 can't be true either. Okay. All right, this doesn't exist, so it can't possibly be equal to f of c. So 3 is not true. All right, so our function is not continuous at x equal 2. Because 2 is not true, it's also not removable. Okay, the next few problems, 13 to 16, we want to circle the conditions that are true. All right, these continuity conditions. Circle the ones that are true for these functions. So let's look at the first one, f of x equals 3x minus 2. It's a simple polynomial, and we're talking about at the value c equal 5 is 1 true, 2 true, or 3. First of all, does f of 5 exist? Yes, for sure. It's a polynomial. The domain is all real numbers, so certainly f of 5 exists. All right, the second one is, does the limit exist? Yes, it's a polynomial. All we do is substitute in 5 to get the limit. So this is yes over here. We'll circle this. And 3, does the limit equal to the value of the function? Yes. The limit is the same as the value. We get the limit by substituting in 5. So the limit is equal to f of 5. So 3 is true. Remember, a polynomial is continuous everywhere. Okay, here, same, we're asked to do the same thing for c equals 3 for this function. Yes, c equals 3 is in the domain. The only x value not in the domain is x equal 2. So 3 is in the domain. The limit as x goes to 3 is obtained by just substituting in 3 here and here. Since 3 is not a zero of the denominator, all we do is substitute in. And f of 3 is the same as the limit as x goes to 3. To figure out f of 3, we substitute in, and to figure out the limit, we also substitute in. In this case, that's rule 3. Okay, so all 3 are true here. All right, let's look at number 15. We're talking about c equal 1. So first of all, we want to know, is 1 in the domain? Well, no, because of this x minus 1 over here, so we don't circle this. Okay, condition 2, does the limit exist? Yes, here the limit does exist. We can factor x cubed minus 1 and cancel the x minus 1 from top and bottom, and we'll see that the limit does exist. All right, so let's look at that over here on a separate page here. Okay, so we're looking at the limit as x goes to 1 of x cubed minus 1 over x minus 1. So the top is a difference of 2 cubes. Let's factor it. This factors as x minus 1 times x squared plus x plus 1. Okay, over x minus 1. Okay, these cancel. And here we get, substitute in the 1 now, we have 1 plus 1 plus 1, we have 3. Okay, so the limit does exist. So that shows that 2 is true, so since the limit exists. So let's get back to this. Here we go. So for 1 is not true, but 2 is true. That limit does exist. And is the limit equal to f of c? Well, f of c doesn't exist, so no, that's impossible. So only 2 is true here. Let's go to 16. C is equal to 3. Okay, if we substitute in 3 on top, we get 15 minus 3 over 12, and on the bottom we get 4. So they evaluate to different values when we substitute in 3. All right, is 1 true? Yes. F of 3 is equal to 4, 3 plus 1. So we can find f of 3. Let me just write that down. F of 3 is equal to 3 plus 1. So that's why 1 is true. Okay, let's look at 2. The limit, does the limit exist as we approach 3? Well, the limit from the left is going to be different from the limit from the right. The limit as x goes to 3 from the left of f of x, that's equal to, substituting to 3 into the top, we have 15 minus 3, we have 12. Okay, and that's not equal to the limit as x goes to 3 from the right of f of x, which is equal to, substitute in 3, we get 3 plus 1 or 4. Okay, this one is, which is equal to 4. Okay, so the limit doesn't exist. So 2, we're not going to circle. And for that reason, we can't circle 3. The limit doesn't exist, so it certainly doesn't equal to f of c. So only number 1 is circled over there.